Hi! So let's continue our discussion on assumptions of linear regression. We have already discussed two assumptions of linear regression in the previous video. Let's move on now. The third assumption of the linear regression is that error terms with respect to the regression line should be normally distributed. Without going into exact statistics, what it broadly means is that if you were to plot all the error terms on a histogram, it should appear like a normal bell-shaped curve with mean 0. Errors which do not follow the normal distribution cause parameter estimations to be unstable. As a result, the coefficients estimated can be misleading. The simple way to counter this is to scale the data to a linear scale using a suitable transformation such as log x, root of x, and x square. The fourth assumption of the linear regression model is that there should not be any correlation between error terms. Now we have already learned that the correlation tells us about the degrees of relation between any two variables. But did you know that there can be a correlation between the error terms too? To understand this, let's take this residual graph as an example. On the x-axis are the fitted points and on the y-axis are their respective residuals. The line passing through the middle represents the regression line. If we look closely, the residuals look completely random and there is no inherent pattern among them. If we choose any random residual point, it gives no information about the sign or the value of the adjacent error terms. Therefore, in this case, the correlation of error terms is not observable. On the other hand, if it is an extreme case of correlation among the error terms as visible in the graph shown here, looking at the magnitude and the sign of any error term, we can clearly get an idea about the next error term. Correlation this strong is usually only visible in the time series data, which is a topic for another day. When the residuals are autocorrelated, it means that the current error value is dependent on the previous or historic values, and that there is a definite unexplained pattern in the y variable that shows up in the errors. In simple terms, it means that the current value of y depends on the previous value of y. But in linear regression, we only model the linear relationship between x and y and not between y and previous values of y. As a result, if errors are correlated, we would misinterpret the model outcome as it missed out on this important information. The fifth assumption of linear regression is multicollinearity. Recall what we learned during the data exploration phase of the independent variable. While checking the correlation between the target and the independent variable, we also looked at the correlation among the independent variables themselves. Whenever we encounter a correlation between the two independent variables to be greater than 0.5 in magnitude, we usually eliminate one of the two variables, because including the highly correlated variables will result in a model with poor interpretation. It is due to the fact that the variation in target variable to be explained by the second variable in the correlated pair has already been explained by the first variable, thus rendering second variable redundant. This phenomenon is known as multicollinearity. For linear regression to work properly, multicollinearity among independent variables must be removed. But which variable should we remove? For this, we will take the help of a concept called variance inflation factor, also known as VIF. Let's see what it does. It is used for diagnosing collinearity or multicollinearity, and it quantifies correlation between two independent variables. The interpretation of VIF is such that higher the VIF value associated with any independent variable, more correlated this variable is with all other independent variables put together. Let's see how VIF actually works. For that, consider that we have 9 independent variables in our dataset as shown on the screen. Now, to calculate the VIF of variable V1 with respect to all the other variables, we will consider V1 as the dependent variable and all the other variables as independent variables. Now, we try to predict the dependent variable V1 with a regression model using all other remaining variables as independent variables and calculate the corresponding R-square score. Now that we have calculated the R-square score, we will calculate the VIF using the formula as shown on the screen. If you notice, lower the R-square score is, lower the VIF value is. A lower VIF means that the independent variable is truly independent and is not correlated with or explained by the other independent variables. On the other hand, if the value of R square is high, the VIF value also goes higher. This means that this independent variable is very well explained using the other variables and can be excluded from our model. This procedure of calculating the VIF is repeated with every independent variable. Although the lower VIF value is considered ideal for any regression model, but VIF of 5 is considered a good threshold. If an independent variable has a VIF value over 5, it is very well explained by the other independent variables and therefore it can be removed. We will see VIF in action during the implementation phase of the linear regression. So this was the fifth and the final assumption of linear regression. With this, we have covered all the assumptions of the linear regression and are now completely equipped with knowledge to implement the regression model.